Next question is, which of the following techniques is suitable to know whether a compound is monomer, dimer or trimer? NMR spectroscopy gives you the information about number of protons and the nature of protons and carbon atoms in the proton NMR and in the C13 NMR. Absorption spectroscopy gives you, means the UV spectroscopy gives you information about conjugation and the oxochromes and chromophores. And IR spectroscopy gives you the information on functional groups, and ESI mass gives you the information about mass spectrometry, means mass of the information about the mass of the compound. Hence, by using ESI mass, ESI means electrospray ionization mass spectrometry, this gives the information about whether the molecule is monomer, dimer or trimer, because it gives the exact mass of the compound. If it is a dimer, if it is monomer, it will be m mass. If it is dimer, the mass is doubled. If it is trimer, the mass will be 3 times higher than the monomer. Hence, we can distinguish monomer, dimer, trimer using ESI mass. Hence, option C is correct. Next question is, the expected proton NMR signals for the following compound is, here there are two types of protons are there, CS3, CS3 and CS3. All these hydrogens having same environment, and here also we have hydrogen, here also you have hydrogen, this hydrogen. All these hydrogens are having same environment, hence these they are chemically equivalent, and these three are also chemically equivalent, so that we are going to get only 2 peaks. And for these peaks, next carbon is not having any hydrogens, hence it will be resonate as singlet. This hydrogen, next carbon atoms not having any hydrogens, this will also resonate as singlet. Option is A, doublet and singlet, both are singlets, hence it is not the option. 2 singlets, so B, answer B is correct. Quartet singlet, triplet singlet. Okay, option B is correct. For this molecule we are going to get only 2 signals, both are singlets. Next example is, in the mass spectrum of compounds given below, which one undergo beta cleavage? That is Mac-Lafferty rearrangement easily. For the Mac-Lafferty rearrangement, usually the Mac-Lafferty rearrangement takes place in the compounds containing carbonyl group, and there must be a gamma hydrogen should be there. There must be a gamma hydrogen. Then only the gamma hydrogen shifted to carbonyl oxygen. Then there will be a beta cleavage takes place. Here there is no alpha beta. There is no gamma hydrogen. Hence this will not undergo Mac-Lafferty rearrangement. Alpha, beta, gamma. Here there is no hydrogen, that is gamma hydrogen, hence this will not also undergo Mac-Lafferty rearrangement. Alpha, beta, gamma. Hence this is having gamma hydrogen, this will undergo Mac-Lafferty rearrangement. This is alpha, beta, gamma. This is having gamma hydrogen, but there is a double bond between alpha and beta bond. There is a alpha beta bond, hence there is no cleavage of this beta bond. Hence this will not undergo Mac-Lafferty rearrangement, that is beta cleavage. See, this type of molecule, the Mac-Lafferty takes place like this. This is same as this. This structure is same as this. This is alpha beta gamma CS3, alpha beta gamma CS3. In this type of, this is Mac-Lafferty rearrangement. So that it will be O dot these two will combine and these two will combine, so that you are going to get this and this molecule. This is the fragmentation patterns. So Mac-Lafferty rearrangement takes place and beta cleavage takes place. This is the beta, alpha, beta cleavage takes place, and this takes place only when there is a gamma hydrogen present. Hence option C is correct. Only the option C compound is undergo Mac-Lafferty rearrangement. Next question is, the characteristic UV absorption of acetone at 190 nanometer and 280 nanometer corresponds to, this one we have discussed in the earlier question paper. 5 to pi star intense band at 190 nanometer for carbonyl or acetone group carbonyl compounds, and N to pi star is less intense band at 280 nanometer due to the N to pi star transition. Hence C and D. Hence option C is correct. That is 190 and 280 nanometer bands are due to pi to pi star and N to pi star transitions. Question is the expected apparent mass of the metastable ion produced when ion having m by z 77 decomposes by the loss of acetylene to m by z 51 will be. Metastable ion is the ion which is ionized after the ionization chamber. While reaching to the detector, it will ionize, so that it is called a metastable ion. The mass of the metastable ion is depends upon mass of this original ion as well as the mass of its mass of the ion which is formed. The equation is means if the M1 to M2, if the M1 ion disintegrate into M2, then mass of the metastable ion is equal to M2 square divided by M1. Hence mass of this metastable ion depends upon both the ion which is formed as well as the ion from which it is formed. Here the M1 is 77 m by z and 51 is the ion mass of the ion which is formed. M2 is 51 square divided by M1 is 77. It will be 2601 divided by 77 equal to 33.77. So mass of the metastable ion is 33.77. Hence it is near to 33.4. Hence B is the correct answer. Next question is, which of the following ketone absorbs IR near 1750? Here they have given 4 options: acetone and 2-methylcyclobutanone, 2-methylcyclohexanone, and 2-methylcyclopentanone. This carbonyl vibrated at 1715, and when it is in the cyclic form, this is the standard value of carbonyl vibration frequency. This is exactly equal to the 6-membered ring. Hence this 6-membered ring, that is cyclohexanone, vibrate at 1715. When the ring size decreases, ring strain increases, S character increases, and vibrational frequency increases. So this cyclopentanone vibrate at around 1745, and this again vibrate more than this because the ring strain is more and S character is more. This may vibrate around 1775. They have given 1750. Hence this is the near value. 2-methylcyclopentanone carbonyl vibrational frequency of 2-methylcyclopentanone is 1745. Hence option D is correct. Which of the following spectroscopy can give bond length in the molecule? Vibrational spectroscopy gives the bond length, but it is not the exact purpose of the vibrational spectroscopy, but rotational spectroscopy is uses for to check the bond length of the molecule. It gives the bond length of the molecule. Hence the rotational spectroscopy is the correct answer, which gives the bond length in molecules. Hence option A is correct. Next question is, the IR stretching frequencies for the compound shown below. You have to assign these frequencies to these bonds. Here we know that OH in the actually the acidic OH vibrate from 3400 to 2400. Broad peak, actually it is 3400 to 2400. Broad peak for acidic OH, and carbonyl vibrate around, acidic carbonyl vibrate around 1710 or 1700, and CN gives a band at 2250 or 2220. Here they have given, and 3000 is for sp2ch, that is sp2ch vibrate at 3100. sp2ch this vibrate at 3100. And check in the options. OH 3300 to 3500 correct. CH3000. Cn is, they have given in the option they have given Cn for 1680. This is wrong answer because Cn vibrate at 2250. OH 3300 to 3500. CH is this is for Cn. OH 3000. CH, no, this is not the correct one because the OH vibrate gives the broad peak. OH broad peak from 3300 to 3500. CH 3000. Cn 2225 and CO is 1680. Hence option D is correct. Next problem is the formation of the base peak in mass spectrometry is due to base peak is due to the abundance of the ions. If the abundance of those ions is more, then that is going to give the base peak. Hence it is give the it depends upon the stability of the ions and radical cations. Hence option B is correct. The formation of base peak in mass spectrometry is due to ionization and stability of the cations or radical cations. Stability of the cations or radical cations. If these are more stable, then they will not further undergo fragmentation, so that the number of these cations or the radical cations will be more in the mass analyzer, and though they constitute the base peak. Hence option B is correct. This same type of question we have discussed in the earlier question paper. The symmetric stretching vibrational mode of CO2 molecule is, if it is symmetric, then there will be no change in dipole moment, hence it is IR inactive, but there will be change in polarizability, hence Raman active. They have given symmetric. If it is symmetric, it is IR inactive and Raman active. IR inactive but Raman active. Hence option C is correct. IR inactive, Raman active. Next question is, predict the normal modes of vibration of HCl, CO2, SO2. We know the formula. That is, if it is a linear molecule, it is 3n minus 5. If it is non-linear, it is 3n minus 6. HCl is a linear molecule. 3 into n is 2. Number of atoms 2 minus 5. 6 minus 5 equal to 1 for HCl. For CO2 is also linear molecule. 3 into 3 atoms minus 5. 9 minus 5 equal to 4. Hence 4 fundamental vibrations or normal modes of vibrations is 4 for CO2. SO2 is non-linear molecule. 3 into number of atoms 3 minus 6. 9 minus 6 equal to 3. 3 is for SO2 because it is non-linear, 4 CO2 and 1 is for HCl. 143. Hence option C is correct. That is 143. Next question is, the infrared absorption frequencies of CCl in halides, C double bond O in esters and NH in amines are observed at. Carbonyl vibrational frequency in ester is vibrate around 1740. So here there are two A and B having carbonyl vibration frequency in the range 1750 to 1730, and option C and D are wrong because they have shown in that option C and D there is a 2980 and 2850. And CCl, the halide CCl vibrate in the lower region, that is around 700 to 600, and NH is vibrate in the range of 3100 to 3500. Hence option B is correct. That is CCl 700 to 600, carbonyl of esters 1750 to 1730, and NH is 3500 to 3100. Next question is, which of the following compound given mass spectrum with relative intensities M plus and M plus 2 in the ratio 1:1? These M plus and M plus 2 peaks arise due to the presence of isotopes. Bromine is having 79N and 81 isotopes. The relative intensity is 100:98, that is in the ratio 1:1. Hence, if there is a 1 bromine, the relative intensity of M plus and M plus 2 ion peak will be 1:1. Hence, the option B is correct. This completes almost all the questions, previous year questions on spectroscopy in KCET exam. Okay, thank you.